Hi everyone, I'm Mona. Today I will share my research progress on sensor fusion for autonomous vehicles. Specifically, I will talk about the implementation and evaluation of the MEP project. Based on my literature review, my motivation is to use sensor fusion because cameras capture rich visual details but fail in low light and cannot measure depth. LiDAR, on the other hand, provides accurate 3D distance but lacks texture and is costly. By combining these two, sensor fusion makes detection more reliable. My plan is to reproduce the MVP project. Based on the paper, we can see that the MVP framework builds on two models, CenterNet2 and CenterPoint. Basically, CenterNet2 works on image detecting objects in 2D and producing instance masks. These masks tell us what the objects are and where they are in the image. CenterPoint instead works on LiDAR data. It processes point clouds to predict object position, size, and orientation in 3D space. MVP actually ties everything together. It's the fusion framework that combines what we get from the camera and the LiDAR into a single, richer point cloud. What makes MVP special is that instead of just stacking sensor outputs, it actually transforms 2D image information into 3D virtual geometry and blends it with real LiDAR. This gives the model more context to work with, especially helpful for detecting small, far away, or partially occluded objects that LiDAR alone might miss. So in short, MVP helps the model see more by making better use of what the camera knows. The MVP paper provides this table showing that the approach greatly improves LiDAR-only detection up to a gain of 6.5 MEP on center point. So I chose to reproduce MEP because I wanted to see how well it performs in practice. Here's my experiment setup and design. The pipeline follows 4 major steps. The first step is to generating 2D detections and then lifting them into 3D virtual points. Next is to combining them with LiDAR and then finally running detection to use the center point. Here, due to the time limits, I only chose a very small mini dataset from New Science. It has only 10 scenes, so it's a very small experiment. After the experiment, I then evaluate the performance on the validation set using standard New Science metrics. This table gives us a detailed look at the fusion model's performance per class. In my case, you can see that car and pedestrian have relatively high MEP and low errors, meaning fusion works reasonably well for them. But for bus, motorcycle, and bicycle, the detection completely fails. MEP is 0 and errors hit the maximum. This may shows fusion doesn't help much for small objects, possibly due to poor visibility in RGB. Also in this chart, the blue bars represent LiDAR-only performance and the green bars represent the fusion model. As we can see, the blue bar is higher than the green bar across every category, which means the LiDAR-only model achieves higher average precision than the fusion model. This suggests that fusion doesn't improve detection in my case, it actually made performance worse. Besides, this chart shows why fusion underperforms in my experiment. Classes like bus and motorcycle have extremely high errors in all dimensions, position, size, and orientation, meaning the predicted boxes were often far off. So while fusion can help when the data is strong, it may also introduce noise and confusion when a signal is weak. So far, my experiment looks not so well based on the results, so here's my outline for my research progress. So far, I've completed the first 2 phases, that is a literature review and a small-scale implementation using the mini dataset. I'm now moving into the third stage, that is to reproduce the full MVP experiment using all 10,000 scenes, instead of 10 scenes only. The next step will focus on analyzing the result, improving the fusion method, and eventually testing how well it can generalize to real-world applications. Thank you so much for listening.